Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm actually pretty excited to be giving this talk here today because the problem that I'm going to be talking about is a problem that I started thinking about actually during the beginning of my PhD. And I had this problem, and I really, really wanted to be able to present it to my qual committee during my qualifying exam. So I worked really hard, but I couldn't really get a result. So I said, okay. Maybe it won't happen for my qual, but maybe in my dissertation at least I can say something about it. 1 year went by, 2 years went by. Dissertation came and went, still no result. And so finally now, here as a postdoc at MSR and working with Yuval and Jian, I'm able to say something about the Converse result here. And so I'll tell you about this long-term problem that I've been thinking about. So before I get into the details, the problem that I'm going to be talking about today is really motivated by developments in the Internet of Things. And today we have these control systems like package delivering drones or self-driving cars or autonomous home systems that sometimes cats ride on that are interacting physically with the real world. And control is a natural way of trying to understand and model these systems. But when we're dealing with these systems, we might be controlling them or observing them over unreliable or noisy communication channels, or the models themselves might not be precise, they might be changing rapidly. And so we need to really be able to understand kind of the fundamental limits on systems like this. So for example, if we were to think about a drone that we're trying to control, but maybe we only have some kind of unreliable measurements about its actual position, yet we want to have it fly in a certain way. How can we understand systems like this? So in today's talk, I'm going to be talking about a very simplified model for problems like this and explore what we can say about this model. So the simplified model is going to take the following form. I'm going to have a system whose state I'm going to monitor, and I'll make all of this precise. And this state will be given, maybe some noisy version of this will be given to a controller. And the controller then wants to put an input back into the system so as to stabilize the system or have the system go according to the trajectory that the controller wants it to go in. So to make this somewhat more precise, let's think of x being the state of the system, and n is a time index. And I really want to think of x as being kind of the error from the desired trajectory. So we really want x to be smaller. We want it to be going to 0. Let's say we have some initial state that's a random variable. x0 is just a normal 0, 1. And the system evolves according to the following equation, that x at time n plus 1 is a times x of n minus this control u of n. So a is a scalar. All of the system variables here are scalars. A is known to us. And this control u can basically be any function of this y, which is what the controller gets to observe about the state x. And you can use memory. It can be linear, nonlinear, whatever. So now the question is really, what is this observation, and how is this observation, what is the kind of thing we're going to consider? So in this setup, in this problem, I want to consider this channel as being a multiplicative noise channel. So I want to think of y as being Zn times x of n, where Zn is drawn IID each time from, let's say, this normal 1 sigma squared distribution. And sigma squared is, let's say, known to us. And these kind of multiplicative noise channels can model synchronization errors in systems, or they can model quantization errors, for example. Or particular kinds of communication that is happening over, for instance, a fast-fading channel. These are the kinds of things that can be modeled and that we're trying to capture in this kind of system. Yeah?
Is Zian assumed independent of the x
Zian is independent of all of the x's, and they're all IID over time. Yeah.
If it was an additive error, there would be a simple solution.
Yes, the additive problem is very well understood. That comes down to basically being a Kalman filter. And there's the additive noise problems actually have been widely studied and are quite understood. But multiplicative problems, or problems where we don't have a precise model, are significantly more challenging. And this is some work that's kind of moving in that direction. So finally, with all of this, what is our goal? Our goal is going to be to make sure that our system error does not grow too large. So in fact, in particular, we want to look at the second moment of the system. And we want to make sure that this is always finite. So this will be our goal going forward. So there has been a lot of work thinking about problems that are similar to this in the control literature. I don't have time to go through all of this, but I want to point out, for example, the Kalman filtering work is obviously very relevant, which considers additive noises. But the one piece of work I do want to highlight is the case where the system state x is observed over a rate-limited channel. So the controller gets a finite number r bits about the system state. And again, the system evolution is exactly the same. Here we have a very nice and clean result that says that this system is stabilizable in that mean squared sense if and only if the information transfer across this channel is larger than log a, which is the growth of the system. And there's a nice intuition about this that I can explain later if people are interested. But with this background, I want to now move towards the bulk of the talk. I'll first talk about a linear achievable strategy to say, how can we possibly stabilize the system, and think about the most simple thing we can do to do this. And then I'll move to the second part of the talk, which will be the converse result, which will be the kind of main heft in the talk. So let's try and understand this problem, and let's say, well, what can a controller do? And let's consider the most simple linear strategy, by which the controller says, well, what do I have? I have y. Let me scale it somehow appropriately. And what's the best I can do, right? Let me not even try and use memory, nothing. Let's do the simplest possible thing. So let's evaluate this. So we just substitute this into our equation. We get the following evolution. And now, when we think about this, well, we're interested in the second moment, right? So let's square this. When we square this, we see that what is really of interest is this quantity, the expected value of a minus d times Zn squared. And this we know exactly how to calculate, right? I can just rewrite this as a minus d squared plus d squared sigma squared. I want now to have this system be stable. So I want this factor to be less than 1. And in fact, I want it to be as small as possible. So what do? I differentiate. I can find the optimal d, right? Nothing complicated, simple stuff. And I solve the equation. I find that d is equal to the optimal d is a over 1 plus sigma squared. Great. Further, I can say, well, when is this factor less than 1, which will tell me when the system is stabilizable using this strategy. And I get some condition like this. This is great, but I want to actually rewrite this condition in a different form. And I want to say that this system is mean square stabilizable using this linear strategy, if and only if log a is now smaller than half log 1 plus sigma squared. And this formula is kind of cute, right? It reminds us of the half log 1 plus SNR formula from information theory. So this is kind of nice. And this cuteness brings me to one of the nicest pictures in the talk. For those of you who are wondering where the title is coming from, we're saying, well, in this regime, the system is definitely not any kind of tiger. It's actually kind of cute and tame if log a is bounded in this particular fashion. So but now that we have this, I guess we can move to the more ferocious part, which is really the converse. So, what kind of converse would we want to have? What would we expect to have? Well, we only considered in the past achievability, we considered this, memory-less, linear, simple strategy. We can actually improve that to show that actually this particular linear strategy is the optimal linear strategy. Memory doesn't help in the linear case. But we don't know if that bound was coming from the fact that, we're only looking at linear strategies, or if some kind of nonlinear memory-full strategy can do much better. So what we would really like is something that says, well, if log a or a is larger than the threshold, then your second moment must be unbounded. It had better explode to infinity. Turns out I'm going to prove a slightly different result. It's actually a stronger result that says that I'll give you a threshold for which stability in any reasonable sense is not possible. And so the statement of the result that we have is the following, is that if a is larger than some threshold that depends on sigma, then for any control strategy, we want to look at the probability of x being bounded within the box. And this probability of it being bounded itself is going to go to 0 for any box that you choose. And so this obviously implies that your second moment is going to be exploding, right? Because you cannot even be within a certain box if you're choosing. So forget anything about the second moment. Which then brings me to the next nicest picture in the talk. This is not a system you want to try and tame. OK, everyone with me till now? OK. So now how do we go about proving this result? And that's what I'll be talking about for the rest of the talk. The first step that I really want to do is I want to think about a reduced system. I want to start ignoring this growth factor a. So I'm going to drop the a here and consider this system with a equals 1. And for the rest of the talk, I'll explore only this particular system. And here what we can see is that if I want the original system to be bounded within a box of size m, I want this non-growing system to fit into an exponentially shrinking box. So I want to instead look at this probability that xn with this system is now in this box that keeps shrinking by a factor a as time goes on. So now that we're looking at this modified system, given that we have all these past results on rate-limited channels and how to understand them, it's natural to think, well, you have some kind of channel here, and additive noise is well understood, as was pointed out. Can't you build on some of those techniques to get somewhere? So the channel that we have is really something like, yn is z times xn. So you can say that log yn is just log xn plus log zn. And if we could bound the rate of this channel, that might give us an approach. But turns out that in our particular problem, the range of xn is actually unbounded. And we don't know what this u can do to the distribution of x, right? Like it can change things in any way. And so getting a bound on the rate across this channel is going to actually be, like we can't do that. So the standard approach of having a rate-limited channel is actually going to be hard. And we can't use this approach. So yeah.
Can you say at least that the posterior distribution of xn is always Gaussian?
No, you can't, because you're adding basically a correlated random variable u, and u, will be dependent on x. And so, like, you don't know what the controller can do.
So the conditional distribution of xn given the entire sequence of u's.
The conditional distribution of xn given the entire sequence of u's will be Gaussian. But
then you take that mixture of Gaussians and you lose.
But you don't actually have Gaussianity, and so you can't actually say anything. OK. So what is the strategy that then we want to look at? And so this was one of the key new ways of looking at the problem. And so the approach to this problem is different from the way control theorists and information theorists have been looking at this problem so far. And what the proof does is actually it looks at this object, which is the density of the system state x at time n. And I'm just conditioning on basically everything that the controller knows up to time n. And I'm looking at this object. And remember, what do we want to do? We want to look at the probability that xn is going to be in these intervals that are shrinking exponentially. So if we can say that actually this density is upper bounded, and we can give some exponential upper bound on this, then we can say that actually the controller cannot know with this exponential precision where the state is. And if the controller doesn't know where the state is, it's not going to be able to hit it and control it, right? So this is the approach that we're going to take to prove that the converse style result. So to do this, we really want to understand the effect of these observations, because that's what's going to make this density become peaky. So what do we want to really understand? Well, we want to understand how does this density change every time the controller gets a new observation, right? Because that's how the controller can do better. So I really want to compare this pink density, which is basically the density based on everything the controller knew at time n-1, to the black density, which is now with the new observation included. And I can just rewrite this as in this form, and now it's natural to want to use Bayes' rule to kind of separate these effects out. So when I use Bayes' rule, I have this pink term, which is kind of the term that I want to relate this to. But then I have this denominator, right? And it's like the density of y conditioned on all the past, and I don't really know how to deal with this. It's something complicated. So we say, OK, let's try and avoid getting into this mess. And note that here there's no term x. So the idea is to just say, let's take the ratio of densities, and so that this denominator term will just cancel out. Because I like this, I like being able to deal with this recursive format. This term I'm going to be able to deal with eventually. So I take the ratio to be able to remove this denominator effect. And so now I want to look at the ratio of the densities of f of little x, given my observations, divided by f of little x at some w, given my observations. And I'm just taking the logs here to make, just to make things a little bit easier. So now my denominators have canceled out. And what I have here in pink is this nice recursive term that I want to recurse on to get my bound. And now there's this blue term here, which is basically the conditional density of y given what x is. But what do we know about y? Y is just a Gaussian times x. And so if I know that xn is equal to some little x, the density of y, this conditional density, is now just the conditional density of a Gaussian, which is really easy for me to handle and deal with. So I can actually explicitly write this thing out. And so it's like, OK, like this I can deal with. This is recursive. We're excited, right? Everyone's excited. We can almost solve this problem. OK. But now what we need to do is we need to bound this term. And we have these things in the denominator. X is going towards 0. And now we have these things that are getting small, that are in the denominator. Finding a bound is suddenly going to be a bit of a problem. So this is where the second idea in the talk comes in, which is that we have a genie that provides side information that helps bound this term in the denominator. And it's interesting how this works. So let me make exactly what is happening precise. Remember that we're proving a converse bound. So if we give the controller some extra information and prove that the controller cannot do anything, that's always fine. You can always give this extra information. So what is this side information we give? The side information is essentially a quantized version of the log of xn. So what we do is we find xn and we localize it in a binary interval between, say, 2 to the minus kn and 2 to the minus kn plus 1. A genie comes along and observes this and hands this kn to the controller. And remember, what was the channel that the controller already had, right? It had log yn is log xn plus some log zn. So it already kind of had a noisy version of the log of x. So it's not like this genie is actually giving that much extra information, but the clever way in which it's used allows us to actually get the bound that we need.
So this interval doesn't depend on sigma. I mean, the y depended on sigma.
The y dependent on sigma, and the sigma will show up in the bound. I'm somewhat suppressing that right now just to be able to give the flavor of the proof, but the sigma does show up. Like these constants will all depend on sigma. Yeah. Basically, like the precision of the observation will dictate the kn. Yeah, exactly. But what this gives us now is this bound on the magnitude of xn. And the way the proof is going to proceed is going to use these cans in a key way. Because now, remember, what did we want to do? We wanted to measure how fast xn was approaching 0, right? And these cans are basically exactly measuring that. So first, they give us a lower bound on xn, which is what we wanted. But secondly, what the problem is now becoming is we want to measure basically how the kns are proceeding. And if we want an exponential bound on x, what we really want is we want now a linear bound on how the kns are increasing. And really what we will be doing is we'll be using kind of the properties of the density of xn to bound kn, and then we'll use kn to bound xn. So it's kind of this back and forth between xn and kn that is going to let us get to the conclusion that we want to. But now, thanks to our nice and friendly genie, we can go back to the proof that where we were and actually have a bound on this term. This trouble has now gone away. And now with some algebra that I'm really not going to talk about so much, we can have the kind of exponential bound that we wanted, which is to say that, OK, the density of x can be bounded basically by 2 to the kn. And there's some constant here, and this constant will actually depend on the z's and on the sigmas. But now, really, the problem now, still, we don't quite understand these, right? These k's are still random. So the question is now reduced to understanding, basically, how do these kns behave? And here I'll introduce the last lemma in the talk, which is that the kns will actually grow at most linearly. In fact, the precise statement that will be that the probability that kn minus k naught is larger than some constant times n, this probability has to go to 0. And the way that we're going to prove this lemma is, in fact, to look at the increments. So we're going to look at kn plus 1 minus kn, and the probability that this is very large. So basically, in one step, these k's grow by a lot. We'll show that this actually is kind of like a geometric. This has these exponentially dying tails. And once we have this, we can have that these kns grow at most linearly.
I mean, if this is very precise, then you sort of know kn, you can ignore y. But presumably, it's not precise enough to do that. Is it?
So
what's the role of yn anymore? I mean, if I have the distribution of kn, it's possible.
Yes. Okay. So it's yeah. I'm like these constants are all not actually constant. There's a randomness.
Oh.
These are random constants that depend on the z's and the y's. So I'm like just in the spirit of giving a flavor of the proof, I'm like hiding those facts. But there's a lot more work that needs to go into actually showing that these things work. But yeah, so we can't actually completely ignore the y's because of that.
No, mustn't be able to.
Yeah. But just to give now, again, like a flavor of how this proceeds, this is the probability we want to look at, which is the probability that kn plus 1 minus kn is larger than L. So what does this mean, right? Kn is basically looking at the order of magnitude of xn. So this means if kn plus 1 minus kn is very large, it means that xn plus 1 must have been much smaller than xn, right? Xn plus 1 suddenly became much closer to 0. In fact, it became closer to 0 by this, factor of 2 to the kn plus L. And how is
Closer by 2 to the L.
closer by 2 to the L? And when is that going to happen? What does that mean? That means that basically at time n, the controller really hit it home, right? The controller got really, really close to xn. So basically, this un at time n was really close to yn. So this was also bounded by 2 to the 2 minus kn minus L. But now let's look at this probability. And this is where all our work on bounding the density of xn is going to come in handy, because u is now measurable by fn, right? U just depends on all of the observations of the past. And so this probability I can just rewrite as an integral of the density of x. And this integral is going to be over an interval j that is basically around x and is of this length. Around un is varying around xn.
2 to the kn.
Un is deterministic now.
Okay, yes. Oh, yes, okay. So we're looking basically at this integral in this small interval. And now we have a bound on this density, right? Basically, we know that this guy is bounded by something like this. We know that the length of j is of this order. And so now we have this expression. These kns cancel. And we get now that the probability we wanted is decaying as 2 to the minus L, just like we wanted. So, which gives us exactly the lemma. And once we have this, we have now proven that the kns increase at most linearly with this known rate, which means that the xn's can decay at most exponentially. And once we have that, basically that gives the converse result. And so just, this bound is far from tight, and there's still some open questions. But yeah.
Maybe your principle that answers my question. I thought on an early slide you presented an only if
for that linear strategy.
Okay.
If and only if for linear strategies.
So you don't know that linear is optimal. You know that it's approximately optimal in the sense that you have a converse.
I don't even know that it's approximately optimal. I have other reasons to believe that it's going to be that you might not be able to do that much better than linear. But I don't have a proof for it at all. I don't know that it's optimal. Like nonlinear controllers can improve by a little bit, but I don't know that they can improve by a lot. I don't know the answer to that.
Thank you, Richard. Any other questions?
Is this paper available online?
Upon request.
Yes, basically, yeah.
Any other questions?
Can you say anything about in your motivation you talk about model misspecification, which in your model I would interpret as something like the constant A is not known, but you know that it belongs to some interval of values.
Can
you say anything about robust control policies that stabilize the tiger for a range of possible model specifications?
So the thinking about actually A not being known precisely is very, very challenging, and there aren't really any results that I know. I know of one classical result that talks about a very limited case of that. I've tried thinking about it a lot, but I don't have a result. Here, the model misspecification motivation really comes from, for example, if you think of the standard Kalman filtering model, you assume that your y is c times x plus some maybe additive noise, and here we're thinking of maybe the c is unknown. This observation gain is unknown. And I have other results that talk about cases where the gain on the controller might be unknown. So you have some distribution on it, but you don't know precisely what it is. It might be changing. So in that regime, I also can talk about some robust control notions. And maybe I can tell you about it offline at some point.
So we'll take other questions in the coffee break. Let's thank